everyone, afternoon, evening, whenever you're watching this. Thank you for coming to my project presentation. I did mine on a mechanized knee brace using Arduino. My class was the INQ 250, and my professor and mentor was Dr. Bala. She helped me to 3D print the pieces from the MCSP lab, as well as Professor Price. So thank you guys in advance. And my name is Alex Hutson. I'm a junior math major and hopefully theoretical data science major as well. And I hope you guys enjoy. Okay, and so here's a little bit of background information on the project. I've been working with Arduino, whether it be Raspberry Pi, the programming aspect, for the last couple of years. And so my father has multiple sclerosis, or MS, which affects his ability to walk or bend, and just kind of affects his everyday movements and lifestyle. And so this project is very near and dear to my heart for that reason. And it came to me about a year, 2 years ago, and just kind of has been on the back burners until I had reached this class. And so this inspired me to begin designing and creating my own version using electronic servo motors as opposed to the neuromuscular electrical stimulation version of my dad's current brace, which basically is like a TENS machine. And so with his inability to really lift his feet or walk successfully in a smooth stride, it stimulates the muscles and kind of does it for him. I would like to create a version that allows him to rebuild those neuro connections and just kind of assist his walking as opposed to doing it for him. So some of the background continued. There have been previous versions used, developed by Sony and various Japanese companies, mostly developed in the order to replace movement for those that have the complete inability to move naturally, whether it be their arms or legs. It's typically a full body suit, bulky, very cumbersome to try to maneuver or live everyday life in. They're also very expensive, whereas mine strives to just kind of assist in a range of motion as well as just help the user walk and kind of return to normalcy. And it's also going to be ideally to where it can be worn underneath the pants and assist movement and give the user a sense of normalcy and not be as noticeable as the full body suit or a exoskeletal style brace. And so my IQ 250 class, like I said, Dr. Bala is my professor, gave me a better understanding of circuitry, how everything works, how each piece works, how they coexist and work together. The circuit varies in these from the ones that were worked on in the class because I use an Arduino Nano board to reduce size to be able to fit onto the brace and be more compact, like I said. In class, we use the Arduino Mega 2560 board. So this is the first prototype. I've got a circuit diagram of the basic servo and infrared sensor set up using the Mega 2560 and the remote control that was used. And here's a real quick video of the first prototype I made that was primarily made out of cardboard, kind of what I had laying around. It was a very rough prototype, but it got the programming and the coding to run and kind of simulate what I was looking for. So here's this. And so there you can see it had the basic range of motion pre-programmed into it from 90 degrees to 120 degrees and then back to 0. So that would represent the standing, bending, squatting, or further knee extension angles. Okay, and here we have prototype 2. This is the one made of 3D printed pieces. Thank you again, Dr. Ball and Dr. Price, for printing this off for me. Huge help. As opposed to the cardboard, the gears allow for a much better transition of the degrees of the servo motor into the brace movements. So here you can kind of see where the brace will go from 0, which would be a standing position, 90, which would be sitting, and 120, which would be a squatted or further extension of the knee, bending angle. And so when played in a fluid motion, it actually will represent a gait or a walking movement. And with some better tuning it would be more personalized to the wearer or user and would help them in their walking, bending, just kind of everyday life motions. And so here we have a real quick demo of it running itself. Like I said, it's just kind of bare bones, bending, standing, that kind of thing. Which right now that's all I'm going for with this model. I plan to scale it up to have a 35 or higher kilogram servo motor that would actually assist the user in movement, as well as a larger brace arms and cross beams, cross straps that would secure the brace to the knee and allow for a much more sturdy movement. So the goal for this project, my end goal would be to, like I said, scale up the model so that it would result in a usable prototype and testable prototype and allow for finer tuning. This will be done by using a harder polymer frame than that of the 3D printer currently, or if I can find a 3D printer that would allow for the polymer frame to be built, that would be a great option. And then, like I said, a higher torque motor would be used, but equally as compact, because like I said, the goal will be to keep it ideally under the pants size and allow for a more normal wearing and less obvious wearing than that of like the exoskeletal style. And then in order to facilitate the higher torque being transmitted to the brace, helical gears would replace the standard tooth gears. This would reduce slipping, stripping, anything kind of related to that standard gear, and it would better translate, like I said, the torque into the brace arms and allow to maximize the ability to assist the user in movement. And so the use of the servo motors in this design was initially due to the ability to set the motor's angle. However, through Dr. Bala's help and some more research on programming the servo motors and everything like that, it also came to me that you can read in from the motor and actually get the angle that the motor is currently at. So this would allow for a better tuning and adjustment to the wearer's gait or walking movement. And so it would better fit that user individually. And here we have my ideal end goal for the brace, again made in Tinkercad. As you can see, each black box on either side will be a servo motor. The one on the outer side of the thigh will be the higher torque motor, whereas the inner thigh will be a much more compact and just kind of assisting motor to keep the range of motion true on both sides. And then you've got the cross straps, which will either be a polymer similar to the brace arms or a neoprene style sleeve. Again, reduce size and keep the compactness and fitting to the thigh much more universal. And then you've got a top view, again, just kind of displaying the general format of it. You'd have the longer section of the brace on the thigh and then the shorter section on the calf with the servo motors on either side of the knee, right on the joint. And then on the right-hand side, you have a snippet of my code. It's basic, like I said, just doing the general motion 0, 90, 120, and set to the infrared receiver and the remote control. In the future, I would love to do a capacitive sensor or a read in and output from the servo motor so that it would naturally adjust and compensate for the user's current movement. Okay, and so here we have the works cited, again, for the patents, the textbook we used in class. Thank you again, Dr. Bala and Dr. Price, for assisting me throughout this whole project, and Dr. Price for printing the pieces. It's greatly appreciated. Thank you guys for watching my presentation. I hope you enjoyed it. Have a great day.